We'll get started in about 1 minute, everybody. Just give people some time to join. Okay, everybody. I think we gave some people to join, but I just wanted to say hello to everybody and thank you for joining and welcome to another John Crane webinar. My name is Ken Sawilczyk and I'm a marketing communications specialist with John Crane, and I'll be your host for the upcoming series of webinars on the topic causes and corrective procedures for identifying and reducing seal leakage. Today's presentation will be the first installment in the series. Sessions 2 and 3 will be held in September or November, and our website will have details on future sessions. We'll have that up shortly. Just before we get started, let me tell you a little bit about John Crane. We were founded over 100 years ago, and we are a global leader in rotating equipment solutions. We have an outstanding reputation for designing and engineering high-quality, durable, customized solutions, and in 2019, we received Frost & Sullivan's Global Mechanical Seal Market Leadership Award. A little housekeeping here. To submit questions, you can submit questions or comments at any time. Please click the Q&A button on the bottom portion of your screen, and if you do have any technical issues, refer to your Zoom registration email. Questions that are not addressed during the live webinar will be answered on an individual basis. We'll address them after the webinar. And registered attendees, you'll receive an email with a link to the recording, and it also can be accessed from our John Crane webinars page a few days after the event. And just to give you some background on the outcomes and scope of this series, like I said earlier, there'll be 3 sessions in the series. So by the end of the series, you'll be able to correctly interpret the signs of equipment issues which may lead to seal damage or indicate that impairment has occurred. You'll be able to adjust the operation of equipment to avoid seal damage, interpret the condition of damage or leaking seal components for yourself, and identify possible causes. One thing to note on that is full diagnosis and repairs should be carried out by qualified John Crane personnel only. This webinar will cover our simple seals that are installed in thousands of pieces of equipment around the globe. These include single seals, rotating primary ring, pusher or elastomer bellows type, and we'll talk more about that terminology a little bit later. As you said here, we'll give you an outline. Today's session, session 1, is a basics of mechanical seal operation. We'll talk about the requirements for long seal life, some of the symptoms of seal distress, how your equipment may indicate a problem, appropriate responses to avoid or rectify an equipment failure, and like I mentioned, we'll have time for questions at the end. Sessions 2 and 3 will get deeper into the interpreting seal conditions and some of the underlying causes. Again, those will be taking place a little later in the calendar year. Today's speakers, is Andrew Filipkowski. He is from our Pasadena, Texas office. He has 5 years experience with mechanical seals and John Crane in various field-based roles. His responsibilities have included seal and support system troubleshooting, seal performance calculations, and seal failure analysis. He holds a Bachelor of Science in Mechanical Engineering from the Georgia Institute of Technology. And industry-wise, he's been involved in pipelines and refineries for the oil and gas industry and the petrochemical industry. And coming to us today from Manchester, England, is Stuart Worthington. He has 7 years of experience in a product development role, working on high-duty sealing and bespoke solutions. His areas of specialty include high-duty applications, designing and developing bespoke solutions, calculations, and troubleshooting. His educational background, he has a Bachelor of Science in Aerospace Engineering from the University of Liverpool. And industry-wise, he's been involved in oil and gas. He is been a maintenance engineer for the railway industry and a product engineer for a pump OEM. And with that, I will turn the control over to Stuart, and he will take you through the first portion of the program. Thank you,
Thank
Stuart.
you, Ken.
Okay.
Yeah, thank you, Ken. So yeah, as Ken said, I'm going to do the first part of the session, and we decided we would kick this series of webinars off by just making sure that we've covered all the basics of how a mechanical seal is working when it's working properly and everything's healthy. Just to really give the basis for when I hand over to Ken shortly, and for the other two sessions in this series, where we then start to look at when some of those things go wrong and how that manifests. So to move us along. So we're going to start just by really covering the super basics of a mechanical seal. We don't want to make any assumptions about how much knowledge we already have for anyone attending this series. So mechanical seal is a component within a centrifugal pump, or it could be many other types of rotating equipment that needs to seal between a rotating or a stationary element within that piece of equipment. So shown here, we have a really simple overhung pump, and we're going to be using this diagram a lot throughout this series. And here we have a representation of the mechanical seal right here, where we have the rotating shaft entering through the stationary body of the pump. So if we zoom in on that area, we're going to assume this mechanical seal, it's a very simple representation. We're going to assume everything here is working well. So we're just going to focus in on each of the elements and understand what is making them work well. So first thing, we have some parts of this, like I said, rotating, and other parts are stationary. So I've just highlighted the shaft in red here to say that this is going to be rotating and the rest of the pump is stationary. So the mechanical seal itself will need to have some rotating parts. So we have this drive element here, and we're representing it with a simple set screw connected to that orange component, which is then going to pass the drive through the other components of the mechanical seal. So what we'll end up with is all these parts here that I've just highlighted in red. So we have everything right up to that blue component, and we can see it's now touching the pink component, which is stationary. So if we just zoom in on that area, so we have contact between a rotating and a stationary components right here on this interface. And that is the main part of the mechanical seal, and we call that the primary seal. So the entire way that a seal works is that the faces on those two components which are touching each other have been machined to be extremely flat. So when those two pieces come together, in this case, the primary ring can rotate while it's touching up against the mating ring, and the gap between those two components is so small, it creates a restriction which makes it extremely difficult for the liquid that's in that pump to escape, and that's how we get our seal. If we just zoom in on those two components that form our primary seal, we have the primary ring and the mating ring. Now, if you've been in the industry for a while, you may have heard alternative names for these pieces. They may have been called face and seat. Some people simply refer to them as rotating ring and stationary ring. But these sort of standardized definitions for these are primary ring and mating ring. So if you were to receive a seal inspection report from John Crane or another main manufacturer, they would refer to them as primary ring and mating ring. If we just look in to, oops, skipped ahead there. A couple of different examples of what primary rings and mating rings may look like. Primary rings typically are longer and thinner, whereas mating rings tend to be shorter and squarer, though of course the reverse can be true. There's an enormous variety between what these two look like, but they will always be present, and one of them will always be able to be identified as the primary ring and the other as the mating ring. The way that we manufacture them to be so flat is through a process known as lapping. So what we're seeing here is a standard lapping machine. The way that it works is we would get the component which needs to be lapped, and we would put it on top of this plate here on the top of the machine with some kind of abrasive compound. As the lapping plate spins, that just slowly, using the abrasive compound, wears away the face until it is flat. And then the way that we measure to check that they are flat enough to be used as a mechanical seal is we use a monochromatic light source. So all the light coming from this light source has the same wavelength. And then we put the workpiece underneath glass optical flat. And what happens is, as the light passes through the optical flat, reflects off the lapped surface and then back to our eye. If it is sufficiently flat, we'll see a pattern of light bands form. You can just see that up on the top right picture there. And depending on the shape of those, that pattern, what the bands look like, we can determine how flat the piece is. So we have the primary ring and the mating ring, and the primary ring is always supported by some kind of load element. Here we're showing it as a single large spring. That load element is absolutely required, and it's required to do two jobs. The first job is it's applying an initial force to hold the primary ring against the mating ring. The other thing it needs to do, as well as apply a force, is it needs to be something flexible, like a spring. Shafts do not stay perfectly still. We'll have small amounts of movement from bearing tolerances, thermal growth as everything warms up when the equipment's switched on. And the other thing that will happen is we may see some wear between the primary ring and the mating ring. So we need the ability for the primary ring to have some flexibility so it can stay pressed firmly up against the mating ring and parallel to it. So it's very important that that is present, it's the correct force, and that everything is free with that flexibility. I also just want to point out that a mechanical seal has more than one seal within it. It has the primary seal, which we're supporting, but there will be multiple secondary seals throughout mechanical seal, and those could be O-rings, gaskets, just making sure there are no other leak paths throughout this equipment. So if I just zoom in on those a little bit more, the secondary seals could have lots of different forms. It's like already covered standard gaskets and O-rings, but it could be something a bit more esoteric, like a PTFE wedge that we're seeing there on the left, or it could be some kind of bellows. Bellows could be an elastomer, it could be PTFE if we need the chemical resistance, or it could even be metal bellows as well. Those load elements, we can see some more examples on the right. So it could be a single large spring like we have depicted here. It could be multiple small springs, or again, it could be something a bit more bespoke, like a wave spring. Or there on the bottom right, we're showing a metal bellows again. The way the metal bellows are welded and constructed, they are sealed, so they act like a secondary seal, but they also will apply a force as well, so they can be a load element at the same time and fulfill both functions. We just look a bit further through the mechanical seal. We already mentioned drive elements before. There could be lots of different types of drive elements in there. And in addition, mechanical seals will always have some kind of adaptive hardware. So here we're pointing at this plate, which is there so that the mechanical seal components can be adapted to suit the shape of the pump that they're fitted in. And if again, we just show a couple of different types for drive elements, we have lots of different potential types. We have set screws like we've shown before. It could be pins through the equipment. It could be keys or ears. And then another one that we're seeing there on the bottom left is pretty typical, a little dimple drive. It's really important that those drive elements are strong enough, but also they don't in any way cause things to become misaligned, and they don't reduce the flexibility of everything. Everything has to still be able to move on those springs. And then on the right there, we're showing the adaptive hardware. Typically, it's things like gland plates, and then also often shaft sleeves, so that we can adapt to multiple different shaft sizes with the same internal seal components. So these components that I've talked about here, every mechanical seal will have all of these components, but they may look very different. Because most seals in the industry should look recognizably something like this one here. But if you just look at a seal drawing, it may not be entirely apparent straight away. But all these present, they must be present, and they must all be operating correctly. Failure in any one of these will disrupt the performance of the seal. So to go a little bit further, what we'll have here is we have the primary ring rubbing against the mating ring, and that will cause friction. That friction is going to cause generation of heat, and it's also going to cause wear. So in order to have a decent seal life, what pretty much all conventional mechanical seals will do is they'll have something called the fluid film. We want to get rid of some of that heat and reduce the amount of wear. So By design, what will happen is a small amount of the process fluid will work its way in between the primary ring and the mating ring, and we call this the fluid film. This is giving us some lubrication, and it's also cooling the faces as well. Now, a consequence of this is that a small amount of that fluid will make its way all the way through the seal and out to the atmosphere and give a small leakage. So all mechanical seals intentionally leak by design. It may be that when you construct seals, you often do not see any leakage. It could be so small it's not visible. So for many people, if they can see the leakage, that's their sign that the seal has some kind of issue, hasn't been constructed properly. But even a seal which is working completely correctly will have a very small measurable leakage. So this fluid film, part of the mechanical seal design process and making sure it's all working well, we have to keep that fluid film correct. If it's too thick, then the leakage will be much higher than we want. We need to control that leakage. However, if we design the fluid film to be too thin, then we're not getting that wear and cooling, so the seal will have a short seal life. So it's the job of all mechanical seal manufacturers is to control that. And then if we look at some of the other requirements on our fluid film, it must be a liquid for conventional mechanical seals. We don't want any solids in there, so we're going to be very careful making sure that solids can't form in there, that if there's any solids in the pump, in the fluid, that we're trying to protect the seal from those fluids. And we can't cook with any gases in there. So particularly worried about pumps being run dry or gases forming across the mechanical seal faces. We also want that film to be really flat and really parallel. That's why we go to such great lengths to machine the faces to be perfectly flat, and we want to keep them flat, which means that the machine itself, we want that to be really well aligned and not too much vibration. We need that fluid film to be stable. Mechanical seals really don't like very transient conditions, vibration, that kind of thing. They work a lot better with a nice stable fluid film. We want the film to be a reasonable viscosity. Again, not too thick because that'll put shear stresses on the faces, and not too thin either because that makes the fluid film too thin. And we need it to be a good lubricant. Some fluids are just better lubricants than others. Ideally, something like a thin mineral oil is a fantastic lubricant. Water will usually suffice, but there are plenty of fluids that we would not want to use as the fluid film in a mechanical seal. So just to kind of summarize that, so for a mechanical seal to be operating healthily, all those key components, they have to be present and they have to be operating well. We need our fluid film, we need it to be present, and we need it to be healthy. We need it to have the right fluid properties. We want the equipment itself to be operating well. And we also want everything to be temperature controlled, not too hot, not too cold. We want the equipment itself to be in good condition, and we want it to be filled with the fluid that we expected it to be, the one that this mechanical seal was designed for. We want it to be running at the pressures, speeds, and temperatures for which the seal is rated and designed. And then finally, a really important note is that the leakage will always be present in a healthy mechanical seal, but within acceptable limits. If a seal has a leakage which is too small, that is an indication that there is going to be something wrong as well. So each of these points, they're all things which are going to come up again, some later today and others later on in this series, where we'll actually see how some of these things can be disrupted, what that looks like on the mechanical seal, and then what we can do to restore them as well. And with that, I'm going to hand over to back to Andrew, and Andrew is going to take you through the next part of this presentation.
Hi, thanks for that, Stuart. And as you mentioned, we're really just trying to understand what's going on within the seal when everything is going correctly, because that is what we're going to look for, and ideally what will be happening. But eventually things are going to start to go wrong, whether it be with the equipment, with the seal itself, something up the line, down the line, somewhere something is going to start to operate incorrectly, and we need to be able to address those, identify those, and then come up with a solution to prevent that from happening again. And all this is going to kind of fall under the umbrella of the overall troubleshooting process. If you've been in the industry for any period of time, you know that pretty much anything can go wrong at one point or another. So in order to identify the problem that is actually occurring, we need to make sure that we're gathering as much information as possible so that we don't overlook anything, nothing gets missed, so that whatever issue we're addressing is the actual issue that was occurring, and therefore we can prevent it from happening again. If we try to rush through the process, we don't get enough information, we run the risk of not correctly identifying the problem, and then down the road we might be running into the same issue over and over again, despite the changes that we've made at that time. So the information that's going to be covered over the remainder of today's session, as well as the future sessions, in large part is derived from the document that's briefly shown here in part. It's available in both a brochure and a poster format. It can be found at the link shown. It's a really good reference document to have in the future if you start running into some of these issues, and you might want to cross-check, what are the symptoms that you're seeing, what are the causes that are related to those, and what are the solutions or the corrective actions that we can take to address that. That's all contained within here. So you can, again, either find it at the address, or if you have a local John Crane contact that you can reach out to, they can also work to help you get this either in a digital or a physical format. So thinking through kind of the process of running into a problem, there's going to be some symptoms. Whether or not we're able to catch those before we really run into an issue is a matter of how big of a problem we're running into, but we'll have a chance initially to observe the equipment externally, which means we're going to be able to use visual indicators, maybe audio indicators. If we have any sort of instrumentation that's taking readings on the pump, all these things can help us address and try to identify problems as they are beginning to occur. Much like understanding the operation of seal, understanding the symptoms that we might see, it helps to start off with what we might see on a healthy seal that's functioning well. As Stuart mentioned in his section, there's always going to be some amount of leakage occurring. We want to keep it within the acceptable range, and which is going to be a little dependent on the type of seal that's being used, what the process fluid is, the operating conditions. The amount of leakage that's acceptable is going to vary from application to application, but for a piece of equipment that's operating within this acceptable range, there's a normal amount of leakage occurring. If it's determined that it's falling within that expected operational range, nothing may be needed at this time. It might just be a housekeeping issue where the leakage needs to be collected and rerouted or managed. But if we look back at equipment performance and history, and this is kind of how we've been operating, and we check with our seal manufacturer, and this is how the seal is supposed to be operating, no actions may be required at this time. However, if we notice, maybe a week, a month, a year down the line, we go back and we look at that piece of equipment again, and we've noticed that the amount of leakage has increased, or we have a very high amount of leakage occurring, we've now crossed that threshold into the unacceptable region, whether it be from emissions limits, if those apply to that piece of equipment, or if it becomes a housekeeping issue, or if it becomes a hazardous issue, or even a cost issue, anything that makes the seal leakage become unacceptable, then we might note whether it's occurring during static operation, dynamic operation, if we notice any changes in the amount of leakage that we're seeing between the two. And those can tell us that there's some components in the seals that we might want to start looking at. So we might want to start looking for things like the seal faces having become damaged, secondary seals being damaged. If there's any hardware problems, whether it be the seal hardware or the equipment hardware. And we're going to be able to start dialing in a little bit, but until we get a chance to actually stop that equipment, remove the seal, and go through and inspect each of the components within the seal, we're not going to be able to tell just yet what the exact problem is. The first thing we want to do when we look at the seal, as Stuart mentioned, we have the primary sealing elements, sealing the primary leak path. So a lot of times those are the first components or the starting point for a seal observation, seal tear down. The information that's listed on here is contained within that brochure and poster that I mentioned earlier. And it goes through and it talks about making observations on the seal faces, what kind of observations you might make. Based on those, what kind of symptoms you might be seeing in the field that will relate to these observations, and then some of the possible causes and some of the corrective procedures that are resulting. So, in the event that we have a piece of equipment operating with a steady amount of leakage occurring with the seal, it might not see a difference between static and dynamic leakage. We take the seal apart and we look at the seal faces. During Stuart's section, he mentioned that under normal operation, we have a rotating face and a stationary face. There's contact occurring there, there's friction occurring there, there's wear occurring there. If we look at the faces and we see the full contact pattern, so it looks like we're making even wear all the way around the equipment, or all the way around the faces. We don't see any signs of high spots, low spots, no excessive damage on the faces. This would be the wear that is normally expected for a contacting mechanical seal. Therefore, if we determine that the primary sealing elements appear to have been operating correctly, we need to start moving back a little bit and looking at the bigger picture. Don't get too focused on the faces, start thinking about some of those other potential leak paths that Stuart mentioned. That's going to get us into those secondary seals, which are sealing all of our secondary leak paths. There's a number of damage or failure modes that can be associated with the secondary seals. I'll start going through a few of them. The first two that we have listed on here, the top picture is an example of some mechanical damage to a seal. It's been cut, it's been nicked, possibly scratched. This is normally going to occur during assembly onto the equipment or installation of the seal onto the equipment, or it could also happen during assembly of the seal. Most commonly, this is going to occur on your O-ring sealing between your seal components on the shaft or the seal sleeve in the shaft, as that O-ring needs to slide a considerable distance on the shaft during the installation process. So if we see this kind of damage occurring, we'd want to check that shaft surface, see if we have any high spots, sharp points, any raised surfaces that we can smooth down and eliminate those that damage occurring during installation. We'd also want to check if we have steps on our shaft, if we have any shoulders, that we have a good chamfer or a lead-in, that we don't have any real sharp 90-degree steps, because those are points where it's very easy to catch or pinch or cut an O-ring. So we want to add those chamfers if they do not exist. The picture on the bottom is an example of extrusion damage. This is not a handling issue. This is actually a damage that can occur as a result of the status of the equipment and also the process conditions. So we've, on the picture on the bottom left, we have a O-ring installed in the outer portion of a mating ring that would be sealing into a gland or a sleeve. And then on the have a cross-section view of what's actually occurring during this extrusion damage. So we have the blue or the process fluid on the left side of that O-ring. That's going to have not just the fluid, but it's also going to have pressure. So it's going to be pushing that O-ring from the side of higher pressure to lower pressure. And then on the right side, we'd have our atmospheric conditions or essentially no pressure. And then we have that small clearance between the mating ring and the surface that it's sealing against. So as that pressure is pushing that O-ring, it's going to try to squeeze it into that clearance. Now, if that clearance is small enough and the pressure is low enough and the diameter of the O-ring is high enough, we won't see extrusion damage occur. But if we get to the point where the pressure becomes too high, the O-ring material itself is too soft, or that clearance is opened up too much, it can allow that O-ring to begin to be pushed into that clearance. Initially, you'll just have some of that material kind of be pushed in. Over time, it can actually start to feather and wear away, which we can see on the picture on the left. Some of the other damage that we might see to our secondary seals. The picture on the left is an example of heat damage or thermal degradation. The component in question this time is not actually an O-ring. This is a elastomer bellows. So the material is very similar, but the construction is a little different. And what has happened is the amount of the temperature or the amount of heat that's being generated by this component is too high. It has caused that O-ring or that elastomer, pardon me, to begin to harden. As it's hardened, it's lost its elastic capabilities and it's begun to crack. All of the elastomer and O-ring materials have upper temperature limits. So we'd want to make sure that, one, that the material that we were selected was acceptable for the maximum temperatures that we would be expecting in the process. And then we'd also want to go back and look and make sure that we're not generating too much heat at the seal faces. That can be transferred back to the secondary seals and cause damages there as well. And then the picture on the right is an example of damage on the top to the O-ring and the bottom to the sleeve. So this would be the dynamic O-ring underneath the primary ring. The primary ring has the axial flexibility with the load element behind it. So as wear is occurring, or if there's any axial shuttling of the shaft, or if there's any change in the loading of the seal due to varying operating conditions, that primary ring is going to move back and forth slightly axially. And as it does so, that secondary seal underneath it, the O-ring, is going to move back and forth as well. If we have a large amount of these cycles occurring, we can start to see that scuffing and fretting wear on the ID of the O-ring in the top picture. And then we can also see where that's occurring on the sleeve below it. This can be accelerated if we have any sort of abrasives present within this process stream, or if the leakage occurring across the seals has a tendency to crystallize or coke or form solids, and then those solids become embedded around that O-ring. So as the O-ring moves back and forth, now those solids are moving back and forth, and we can see this wear on the sleeve. So if we start to see this damage, we might want to consider one, adding a coating to the sleeve to prevent that wear from occurring. Depending on the process, we might also want to consider switching from a pusher design to a non-pusher design, if that's a possibility. With a non-pusher seal, secondary seal, we have now made that contact point between the secondary seal and the sleeve static, and then the rest of the secondary seal is flexing to allow the axial flexibility for the primary ring in that seal head assembly. Other damage that can occur to an O-ring can be a result of chemical incompatibility or chemical attack. We always want to be aware of the process conditions, and especially if we have a mixed stream or a mixed process fluid, we want to be aware of all the different constituents contained within that stream. There's a wide variety of secondary seal material choices, and that exists for a reason. There's a wide variety of process fluids that we need to seal, and not all those materials are going to be compatible with all those process fluids. So we need to be mindful of what we're putting in a seal in a given application to make sure that it's compatible. If we take a seal out and we see some of the damage that's occurring here, that would be a sign to us that that we've run into an issue with incompatibility. On the picture on the left, we have two O-rings. The one on the bottom of that picture is the original O-ring as it would be installed with its nice circular cross section. And then in the top part of that picture is a O-ring that has been chemically attacked and has actually started to degrade, and you can see it separating there. That's not the only damage that you might see. On the picture on the right, we have two O-rings again. The rightermost or smaller O-ring is the original O-ring as it was designed, and then the leftmost O-ring or the larger O-ring is the O-ring that was removed from the seal after it was pulled for repair. What has happened here is a swelling has occurred. The O-ring has increased in size and in cross-section, and this would be another sign that we would need to consider changing the O-ring material in this case. One other thing that can occur is explosive decompression. This is going to be most common on high pressure applications or volatile process fluids. These O-rings are not impermeable. It's possible for the process fluid to get under the surface and get into the O-ring. And in volatile surfaces that are at high pressure, the pressures help keep that fluid in a liquid state. As long as it's liquid in the O-ring, it's not much of an issue. However, when that pressure is removed, that liquid now wants to become a gas. Depending on how quickly we're removing that pressure, if the liquid does not have enough time to get out of the O-ring before it vaporizes and begins to expand as a gas, it can expand within the O-ring and cause these ruptures or these cracks that propagate from the inside of the O-ring out, and you could have a rapid failure of the O-ring. If we're seeing this damage occurring, we might want to consider one, if there's a possible way of slowing down that depressurization, if it's possible to go through a more gradual depressurization process, or we could also switching to a different elastomer grade. There's many different elastomer grades that are ED resistant or specifically designed to resist explosive decompression. So that's something that we could consider as well. The failure or the possible causes and the symptoms I discussed previously. This is another snapshot from that brochure and the poster that I mentioned earlier. It has a very helpful chart on it. It talks a lot about the slides that I just covered, and there's other parts of the graph that'll cover the slides in the rest of this session and in the future sessions. But it's a nice checklist to help you start off with a symptom. So what are you seeing in the field? And then go through a list of possible causes. So we've identified the symptom in the field, we've pulled the equipment for repair, we've pulled the seal for inspection and repair. And as we go through, we can start matching up some of the possible causes based on the damage that we see in the field to the symptom that we were seeing in the field. And then once we've gone through and identified those possible causes, we can then look at our corrective procedures. So we can start dialing the first thing that we saw into the field. What can we do to address this? And all through this process, following any thorough troubleshooting process, we want to follow this kind of process to make sure that each step is connected to the previous step, so that eventually the recommendations and whatever changes we're making in the field are following a logical logical progression, so that we're actually identifying the right issue. But again, a very good reference document to have in the future that covers a lot of what we're going to be going over in these sessions. Some of the other symptoms that we might see in the field, we might not see that steady leakage anymore, or that high leakage anymore, but we might start to see intermittent leakage. We might also have some audio cues with that. We can see the seal spitting visually. We might see intermittent amounts of leakage, high at one point, low or even no leakage at another point, but it kind of comes and goes. And then with that, we might be hearing some stuttering or even some popping from the seal as well. This would tell us that we have the seal fluid vaporizing from the seal interface. As Stuart mentioned in his section, we have liquid being used to lubricate the faces. When we avoid having gas between the faces mixed within that liquid. So this would be a sign that that is now occurring. If we're seeing this, we might want to consider cooling the seal faces. If we keep the seal faces cooler, we keep that fluid between them cooler, and we decrease the chance of vaporization. We'd also want to go through and check our seal flush system. We'll talk in greater detail later about some of the troubleshooting that's involved with seal support systems and their various kinds. But if we have a flush being supplied to the seal, we want to make sure that it's operating correctly and we're getting enough flushing and cooling to the seals. And if we find that it's not, it might be a simple fix of just increasing the flow rate if we determine that it is too low. We could also hear squealing. If we hear squealing, we're now seeing very hard contact between the seal faces. That's a sign to us that we don't have a good lubrication anymore. We're getting hard contact between the faces. We have solid on solid contact. So again, we want to check to make sure that we're providing enough lubrication, checking our seal support system, making sure that it's operating as intended, and see if we can increase the flow rate or improve the quality of the flow to the seals, and see if that makes that noise go away. Something that we visually see on seals from time to time is carbon dust accumulation on the atmospheric side of the seal. You can see it on the back of the gland or on the collar. Typically going to be a very dark dust accumulation at those locations. This would be a sign that the inner or the primary ring face, which is typically going to be our carbon face, is seeing rapid amounts of wear, and we're seeing this carbon dust begin to accumulate now on the outside of the seal, which would be another sign that we're not getting enough lubrication. We're getting excessive wear of the faces. We want to go through and check our seal flush system in these scenarios as well, to make sure that we're getting enough flow and enough lubrication to prevent this, getting a good lubricating fluid film back between those seal faces. One other thing that can cause this to occur is if we exceed the pressure limits of the seal. So we're increasing the load on the seals to a point where it's not able to operate adequately anymore, and that's causing the rapid wear as well. So we want to go back and check our operating conditions and see if anything has changed within the system to increase the amount of pressure that the seal is seeing. Other observations we can make might not be direct audio or visual checks on the equipment itself. It might be something that you notice looking through repair logs or just having dealt with the equipment. But we notice that we're seeing short seal life. That's going to be measured by how often the seal or the piece of equipment is being pulled from repair. This is normally measured as MTBR, or mean time between repair. And if we notice that the amount of life that we're getting is inadequate, this can be caused by a number of things. So if we have abrasives within the process fluid, we have these hard particles that are getting between the seal faces and causing a rapid amount of wear. That can lead to short seal life. If the seal is running hot, if we take the seal apart and we've noticed a lot of thermal damage either on the seal faces or on the secondary seals, that can lead to short seal life. And then there's a number of issues that are tied in with equipment alignment as well. As Stuart mentioned, we're attaching rotating components of the seal to the rotating components of the equipment that the seal is installed on, and then we're attaching the stationary components of the seal to the stationary components of the equipment. So the alignment of the equipment's rotating stationary components is going to directly affect how well aligned the seal faces are. And as Stuart mentioned in the section, we need those to be not only very flat, but we need them to be operating parallel to each other. So alignment becomes a very big concern with seals as well. Any of these options, if we see them, if we have abrasives, can we look at removing the abrasives, whether it be through filtration or some sort of separation, or a strainer to remove those, or can we look at an alternate flush source and alternate seal support system? If we're running hot, making sure that we're providing enough flow, enough cooling, enough lubrication. I've hit on this point a few times within the various symptoms, but it's something that's very, very important with contacting mechanical seal designs, that we're making sure that we're getting enough cooling and enough lubrication of the seal faces. And then we also want to check the equipment alignment and condition. When the equipment is coming out to look for any issues, also check the equipment as it's going back in, so we have a record of as found, as built alignment conditions. And again, all of these symptoms that we might be seeing in the field are tied to possible causes, and all of those possible causes are tied to corrective actions to address those issues. They're all found within the reference document that I mentioned earlier. So after the session today and the future sessions, it's a very good reference document to have on a day-to-day basis to be able to tie back in when you see these issues in the field. Going through and covering all the symptoms that we talked about: squealing, carbon dust accumulation, various amounts of various levels of seal leaking, whether it be within static conditions, dynamic conditions. There's no other symptoms within the seal that anything's going wrong. And then running into various amounts, various types of short seal life that aren't tied into high or intermittent leakage or any of the other symptoms that we talked about. And at this point, I will hand it back over to Ken.
Thanks, Andrew and Stuart. That was a very informative presentation. And just a reminder, if you do have any questions, click the Q&A button in the lower portion of your screen. And we do have a few that came in during the program. So I will take a look at here. A couple of related ones. Stuart, when I send this over to you, just I guess a two-part question here. What is an acceptable amount of seal leakage, and what is the impact of a small amount of leakage?
Sure. So I guess, yeah, this question is quite common. Yeah, how much leakage is the right amount, is too much? And at risk of giving a dissatisfying answer, the answer really is that it greatly depends. Mechanical seals are extremely sensitive to very small changes, which can have a significant impact on leakage. What I can say is that many mechanical seals, sort of 90% of them out there in the field, working in the general industry, you're looking at measuring the leakage in a few grams per hour. Well, that's small enough that if it is a fluid like water, which could evaporate, it'll probably evaporate as quickly as it leaks out, so you may never see that leakage at all. Whereas if it's an oil, you know, that it's not going to evaporate, so it will just slowly collect, and you may see that as you know, the occasional drip, and again, you know, maybe a few drops a minute. But it'll be really important here to understand what is the particular leakage which is expected for that mechanical seal. And you can get that, it's often in the data sheets for the mechanical seals themselves. There'll be some method to estimate your expected leakage, or directly contacting your mechanical seal supplier. One thing which is really important to understand is that any leakage values given, there will always be an estimate, because any small change can have a decent impact. And also, one other thing to remember is that when a seal is first installed, the leakage will typically be higher while the face is bed in, and then the leakage may settle back down again after the first sort of 50 to 100 hours. In terms of the impact of the small amount of leakage, is typically negligible. So again, if you're talking a water duty, a few grams an hour, the pump's not going to notice that it's missing that fluid, and you're not going to notice if it simply evaporates away. However, for a fluid like an oil that's not going to evaporate, you do need to have some kind of drain mechanism so that leakage can be safely just collected and sent to a safe drain. However, it is important to note that some fluids, when they leak across, that leakage could have some kind of greater impact. So if a seal supplier is sent an application and told to select a seal for some kind of fluid which could cause environmental issues or could be harmful or flammable, we won't simply put a single seal on there. We'll be aware that it's unsafe, or could cause some equipment damage if that fluid is allowed to simply leak to the atmosphere. So that will basically be solved by a more complex, some kind of secondary containment or a much more complex flush plan, which will mean that we can actually eliminate that leakage completely. But for most simple applications, it's very negligible effect.
Okay, thanks to Stuart. Quite a few questions have come in. We'll address as many as we can. Andrew, why don't we send this one over to you, but what are the most common causes of seal failures?
Right, so the most common ones are generally tied to a change in the operation of the equipment or the operation of the support system, but something that's going to affect the mechanical seal. Stuart covered during his section that there are all kinds of process conditions that need to be taken into effect when selecting a mechanical seal for an application. So we want to know the process fluid, temperatures, operating speeds, pressures. All of this needs to be taken into account. And a lot of times what we see is a seal that was designed for a certain application or for certain pressures is exposed to different temperatures or different operating speeds or different pressures or changes in flow rate of the support system. And all of these changes can quickly affect how well that seal is performing. And most often that is what we see cause seal failures or cause seals to be pulled, is that the design and operation point for that seal has now shifted. It's being put into a different kind of operating mode, and it sees a change in performance and sees a change in the amount of leakage, and then the equipment gets pulled as a result.
Okay, thanks, Andrew. I think a couple questions had come in on this. So Stuart, why don't I send that one over to you? This one is, can any monitoring be done to prevent seal failures?
Yes, absolutely. So it is an unfortunate truth that many seals, there is no monitoring at all, and the monitoring is someone noticing on a site walk around the mechanical seal is leaking. However, there are certainly early warning signs, some of which can absolutely be picked up with equipment. And the big one for us is going to be some of the equipment that you may already have monitoring, the wide of the pump or the machine which the mechanical seal is attached to. So for example, if you're monitoring the pressure and temperature of the fluid within the equipment, if there's any deviation from what it's supposed to be, particularly higher pressures and temperatures, usually danger zones, then my recommendation would be to detect that and correct it before there's an issue with the mechanical seal. And another key one would be vibration as well. If you're seeing high vibration, that could be an indication of a number of problems, degradation of the bearings, insufficient alignment of the pump. All of these things will have an effect on the seal and could cause shorter seal life. So if you're seeing any of those alarm signs, don't wait for your mechanical seal to start leaking or show a problem. Attend to it straight away, and that'll maximize the seal life and potentially prevent an equipment failure.
Okay, thanks, Stuart. Quite a few questions that have come in here. We've got, it was 45 minutes, we're a little over, but we'll try to address a few more if people are willing to stay on. Andrew, I thought this one might suit you. Somebody suspects that there is a possible problem with a seal. What are maybe the first general steps that they should perform to troubleshoot that seal?
Yeah, that's a good question, because a lot of times I know in my position, I'm sure Stuart got these questions as well, where you kind of just get a question that from a customer saying, my seal is leaking, what do I do? And as we talked about in this session and in the future sessions, a lot of things could possibly lead into that. So if you've identified that a seal is leaking and you still have a chance to go collect information at that time, that's a very good opportunity to first off go out and look at the equipment. Can we both quantify and qualify the leakage? What amount of leakage are we seeing? Where are we seeing the leakage occur? Are we seeing it at certain conditions and not other conditions? So at that point, we'd also want to look at what are the operating conditions of the equipment at that point. If we can note down suction pressure, discharge pressure, the operational speed of the equipment, or if it's actually in a static condition, all of those pieces of information would be useful. And then whatever information we have about the process at that time, as far as the process fluid, the temperature, but also the process if it's tied into a unit, what's going on upstream and downstream of that piece of equipment. All of that is very, very useful to help later on down the line be able to tie back into what we think the most likely and most probable cause was.
Okay, thanks, Andrew. I have time for I think one or two more here. I guess, Stuart, let's see if you can address this one. When assessing a used worn seal face, how would you measure the seal face for high or low spots?
Sure, absolutely. So one thing is that you may physically be able to see it with your eye. And in fact, this is something which we're going to address in session 2 of the webinar. We're going to look at this more closely. And we've got a couple of great images, I believe, of so where the high and low spots, you can physically see where some elements of the seal have had more wear than others. But then we also have tools as well, which we can use to actually then measure the extent of those high and low spots. And that can also help us to determine what may have caused those high or low spots. We can identify, was it maybe gland bolts were over tightened, or something else somewhere in the way that everything was assembled and set up. So yeah, visual, and also we can measure it in our materials labs as well.
Okay, thank you, Stuart. I'll take one last one here. Andrew, if you can address this one. Why carbon is carbon preferable material for the primary ring? Do you have any information, any insight into that?
Yeah, so I think most people who have worked with mechanical seals for any amount of time have probably noticed that carbon is a very common material for the primary ring, and there are a number of reasons for that. With all materials for mechanical seals, and definitely with materials for the faces themselves, manufacturability is one of the main points that we want to look at. So are we able to form it into the geometries that we want? As Stuart mentioned, the primary ring typically has the more complex geometry. We're designing it in certain ways to be able to handle the closing and the opening loads that are being implied by the pressure within the process fluid. So our ability to manufacture it is a big point. But then during operation, we want to take advantage of a couple factors within carbon. One, it's relative a neutral material. It's not going to be chemically attacked by a wide range of fluids. And then also it has very good wear properties. So as it is mating up and operating against the mating ring, it'll wear nicely and evenly, but at a very controlled rate. And that wear also helps promote a little bit of self-lubrication when we might run into intermittent amounts of dry running or possible vaporization. So it's a very manufacturable material, and it's also a very good material for its wear properties when used as a primary ring.
Okay, well, thank you. I guess we were about 10 minutes over, so that's all we have time for today. But there's quite a few questions that came in. We will, go through these and respond to you individually, via email and get you your answers within a few days here as quickly as we can. I just want to thank everybody for taking time out of your day to spend an hour or so with us to listen in. I hope that you enjoyed the program and learned quite a few things out of it. And like I've mentioned a couple times, and some of the speakers have mentioned, there'll be 2 more sessions. One held session 2 will be run in September. We'll give you exact dates and information for registering. Watch our website, your inbox, and our social media accounts for more details on that. Also, session 3 will be held in November. So again, appreciate everybody joining, and really look forward to speaking and interacting with you. So with that, I will conclude the program, and thank you again. Have a good day, everybody.